If we really think about what sort of changes for us biochemically, sort of day versus night, well, we do have to think about where we're getting our energy from, right? Because during the day, we might be eating food. So we've got, fuel that we're bringing in. And at nighttime, we don't have food that we're bringing in, so that we need to break down fuel reserves that we have to be able to utilize those for energy. But at its core, the biochemical pathways are really the same for what we're using to sort of generate energy for ourselves. What's really neat about plants is because they have those two different organelles, chloroplasts and mitochondria, they have different options for producing the energy that they need. So what I'm going to do here is just kind of compare and contrast what's different with plants day versus night. And at the end of the day, it really sort of comes down to what organelle is really doing chemistry. During the day, it's going to be chloroplasts, because chloroplasts can generate the ATP and the NADPH that plants need to do whatever they need to do. At night, when their sun is not out, they must rely on mitochondria to produce ATP and NADPH in the same ways that we do. So, kind of drawing just our little generic plant cell here and highlighting that during the day, it's going to be focused primarily on using its chloroplasts. So I'm going to draw a chloroplast here, kind of trying to draw my grana that I have there. And then at night, we're going to be using mitochondrial biochemistry. So let's talk about what those biochemistries are. Kind of, again, 30,000 foot view for what's happening here. Now, energy during the day comes from the sun, right? We've got the sun sort of providing sunlight in the form of photons. When those photons kind of are used by chloroplasts, that's what powers our light reactions. And here's a good summary again of what we make in our light reactions, right? We evolve oxygen, but that's not really anything that's a benefit to the plant, right? That's benefit to us and the rest of the planet, right? But the important things for the plant is it generates ATP and NADPH. Okay, so ATP being our biological money, NADPH being sort of an electron store that it can use for any reductive biosynthesis that it needs. So at the end of the day, what happens is this NADPH and this ATP is going to service the cellular needs of a plant, but it's also going to be things that are used in the Calvin cycle. And I'm trying to switch over to kind of using Calvin cycle exclusively rather than calling them the dark reactions, or more appropriately, the light independent reactions, which is just confusing sounding. So we're going to call this the Calvin cycle. But remember, this is where we're going to take and fix carbon dioxide as carbohydrates. We need ATP for that, and we need NADPH for that. So we need that money, and we need those electrons as glue to hold those carbon atoms together. Okay? Oops, that's supposed to be red here. But at the end of the day, we are making carbohydrates. So to summarize, what plants do during the day is they use this wonderful energy from the sun to provide ATP and NADPH that not only serves their cellular needs, but allows them to generate fuel reserves for themselves through the Calvin cycle chemistry by fixing carbon using the money from ATP and NADPH. Okay, so what do they need to do at night? Well, at night, they are going to need to tap into these fuel reserves. So I'm going to highlight that for plants, these carbohydrates are their fuel reserves. So not unlike we synthesize and store glycogen as a way of having a glucose reserve, plants synthesize these carbohydrates as a way of having a fuel reserve for themselves. So at nighttime, what's going to happen is the mitochondria is going to have to start doing chemistry, and it's going to be doing the same biochemistry that we've learned about, and it's going to be using those fuel reserves to do biochemistry that we're familiar with. So let's highlight what that biochemistry is. Again, we're going to be able to use glycolysis because we're talking about essentially glucose that we need to break down. So we need glycolysis. We're going to have the citric acid cycle, electron transport, oxidative phosphorylation, right? Those latter two we don't do until we dip into the mitochondria. And that's going to make ATP, CO2, and water, right? That was our main fuel equation. We've got fuel plus oxygen generates ATP, CO2, and H2O. So plants at night, to satisfy their cellular needs, are going to be able to make ATP. If we remember, how do we make NADPH? Right, that's the pentose phosphate pathway. So during the nighttime, plants are going to use those carbohydrates that they've sort of stockpiled. They're going to use their mitochondria and biochemistry that we're very familiar with to go through processes that generate ATP and NADPH. And again, the reason that they're doing this is for their own cellular needs. Now, what we have to make sure does not happen, okay? So we do not want these ATP and NADPH to come over here. We do not want to be using ATP and NADPH that's derived at night. There's still going to be carbon dioxide that's certainly floating around in the atmosphere. We do not want to be activating the synthesis of carbohydrates at night. Well, what this means has to happen is that must mean we need to inhibit the enzymes of the Calvin cycle. Okay, so moving on, in another video, we'll talk about the details of how we inhibit some of the important Calvin cycle enzymes. But the key piece here is that the Calvin cycle cannot operate at night. Otherwise, that would cause that futile cycle. Remember, a futile cycle is where we're going through sort of anabolic and catabolic processes kind of at the same time. So we do not want the Calvin cycle to be undergoing chemistry and synthesizing carbohydrates at the same time that those carbohydrates are being broken down into ATP and NADPH, and then just reusing that catabolically derived ATP and NADPH to remake carbohydrates. That would be a futile cycle. So in our next video, we're going to talk about how we control those enzymes of the Calvin cycle.